Hi, I'm Mr. V, and today we're talking about illustrative mathematics, which is our text, Unit 4, which is about right triangle trigonometry, and this is Lesson 4, Ratios in Right Triangles. And by the end of the lesson, you should be able to build a table of ratios of side lengths of right triangles. So for the bell work, we considered this ratio, which one is greater, and are they equal? And you'll notice we have two angles here that are identical. So by the angle-angle triangle similarity theorem, these two triangles are similar, which means that their angles are congruent and their sides are proportional. So you could write A is to B as C is to D. Or you could write within the triangle, A is to C, the short leg to the hypotenuse, as B is to D, the short leg to the hypotenuse. If you were to try to convince someone who thought BD was greater because the triangle was larger, how would you do that? You're supposed to think of your own ideas. And when you press here, this gives you some other ideas. Maybe you take measurements of A, B, C, and D and then plug them in to see if it works. Maybe you look, the triangles are similar by the angle-angle triangle similarity theorem. So A is to B as C is to D, which means that A is to C as B is to D also. Maybe you say because the angle-angle triangle similarity theorem, so that B is some scale factor of A, and D is that same scale factor times C. So for some scale factor of K. So A is to C as KA is to KC, which means that B is to D. Another way to possible argue this. And finally, you could have said that the side lengths are proportional within or without the between the triangles, like I said at the beginning. For this activity, tons of triangles, we had some instructions. We had to go to this document. And in this document, there were several instructions. And if you read these carefully, you'll understand what's going on. You're to work in groups and use this applet. Now this applet, I can't see what you're doing while you're doing, but I can imitate it. So if I have an angle, say I'm given 10 degrees, I can move A to make this a different size. I can make it, say, 10 or 10.7. From this angle, this 10-degree angle, this is the adjacent side. The opposite is over here, and this would be the hypotenuse. So you were to record your values in a table with your partners. Which partner? 1, 2, 3, and 4. And everyone gets to record their numbers. You can see how when they do the per ratio, even though they have different side lengths, nobody's doing the same, everybody has adjusted their triangles with this A point to be something different. But when they record their ratio, their side lengths, and actually calculate the ratios, they come out the same. And this is for 10 degrees. Notice it's 0.8 and 0.17. When I do its complement, which is 80 degrees, I get 0.17 and 0.98. Or here's another one. This is 20 degrees. I get 0.94 and 0.34. And then when I do this one, I get 0.34 and 0.94. And if I take this number and take 1 and divide it by this number, I'll get this number. Or if I take 1 and divide it by this, I get its opposite. So the opposite over the adjacent over the opposite. Why is that? Well, in a triangle, if I have a right triangle, and from this angle, if this is the opposite divided by the adjacent, opposite divided by the adjacent, for this angle, angle 1, is going to be x over y. Well, for angle 2 up here, the opposite divided by the adjacent, I'm sorry, this should be y over x. What am I doing? The opposite over the adjacent. Opposite over the adjacent. So the opposite of angle 1 is y, the adjacent is x. For angle 2, the opposite over the adjacent is x over y. So these are flipped, these are reciprocals. And if I use h as my thing, from here, this is the opposite over the hypotenuse. From here, this would be the adjacent over the hypotenuse. So you can see that they're just backwards. They're just switched. Why is that? Well, because they're complements of each other. These two angles add up to 90, and the three angles add up to 180. Oh, that's not a very good explanation, but you can see here, for angle 3, I have 0.34, 0.94, and when I switch them, I have 0.94 and 0.34, and this person made a mistake. So try to watch for those as we're doing them. Anyway, this is an activity where we're building this table and exploring it. We shared out our experiences. So when we have tons of ratios, here we have all these ratios. Compare the row for 20 degrees and for 70. Notice these are complements of each other. The adjacent to the hypotenuse here is 0.94. From 70, that would be the opposite to the hypotenuse. Just like I told you, they switched. 0.342, 0.342. And this, if you take 1 over this, you will get this number. Same here. For the row for 55 degrees is given here. Complete the table for 33. Well, if I were to draw this figure, so I'm going to copy this over to my whiteboard. I'm going to draw a picture of this. Not that way. Excuse me. Draw a picture of this. If I have 55 degrees here, and I have 35 degrees here, the ratio of the from 55, this is the adjacent, and this is the opposite. But notice from this other angle, from up here, this would be the opposite, and this would be the adjacent. So if I'm looking at the opposite divided by the adjacent for the 55, that's the same as the adjacent divided by the opposite for the opposite divided by the adjacent for the 55 is the same as the adjacent divided by the hypotenuse, the hypotenuse, whatever it is. Here I'm going to have 1 over 1.428. And I don't know what that is out of my head, but I'm going to put these in the opposite places. And just know that these tables have been around for a long time, for centuries. And when I was your age, we would have to use tables because we didn't have calculators. So we'd have a book of trigonometric ratios and up to the 10th of a degree. And I was so proud of that book that I had, and I got it from the library, but it was like, wow, we don't use that anymore. We use calculators, or we use some other way. So here we have 0.389. 0.389 is the adjacent to the hypotenuse. Adjacent to the hypotenuse. Oh, it's not on the table. What does this tell us about this number? 0.839. 0.839. It's going to be between 30 and 40 degrees. I don't know how much, but we can say it's going to be between. That's about the only thing I can say with this table. Here we have what are the possible ratios, what it would look like. We have some more activities. And this is something for you to read on your own. This is like an activity synthesis for this lesson. And here's the lesson synthesis. People have made tables for thousands of years, using the table to come up with unknown angles. Think about the patterns that you noticed today. Notice how these two flip. These two flip. I don't know what this number is. Adjacent to hypotenuse, 0.421. It might be like between 60 and 70. Maybe it's 65 degrees. And if this one is 65 degrees, so I should use my marker tool. If this is 65 degrees, then how much is this one? Let's see. The adjacent hypotenuse is 0.93. It better be the complement of 65, which would be 25. And sure enough, it's going to be between these two numbers. So it'll be somewhere around maybe 25. And I don't know exactly what it is, but I'm just approximating based on the table that these complementary angles switch places with their opposite and adjacent sides. For the cool down, let's see here. So we can cool down. There's a plane here. You're going to have a ratio of the opposite to the adjacent leg. And you can look this up in one of your tables to see if you can come up with the opposite to the adjacent leg of 0.25, somewhere between here. So it's probably around 15 degrees. I don't know what it is. I'm thinking it's around 15. Lesson summary, and that's all I've got for you for today. Please read through the summary and check it out. And remember, our objective today was to build a table of ratios with side links. Using those is not something I'm expecting you to do just yet. We will be using them all throughout this particular unit. Good luck and success.